All right, last topic that we're going to talk about with mechanical waves. What else is there? Well, we can talk about boundaries. So we've imagined a string that's just lying on the ground or that's floating in space and ignoring gravity and all that. What happens if one end of the string is fixed to a wall? So what happens if you have a string that's fixed at the end to a wall? And I'll use gray to denote that it is fixed there. So what if we sent a wave pulse down that string? If we do work on the free end of the string, on the left side, so as to send a wave pulse down the length of the string, the wave pulse, interestingly, reflects back towards us. And maybe this isn't too surprising because waves reflect. You probably know this from electromagnetic waves. That's how light works. And we're going to get into that later. Because waves reflecting off of surfaces is the only way that we hear sounds. It's from around the corner or from a source that's not directly to us. And it's the only way that we see pretty much all objects in our world. It's reflection of the light. So, if we sent a wave pulse down here, we would do subsequent ones. We would start this wave pulse here, and it's fixed, and I'll just not draw the wall, but it's there each time, and it's got velocity that way, right? So now, as it approaches, it's traveled this distance, and it's fixed still. So what happens when it hits the wall is one last one here. There's this violent reversal process. So maybe there's one last little bit of motion there. And at the right moment, if you were to catch it, there's nothing going on for a split second at the moment that it's reversing. But at this moment, there's a force upwards, the string on the wall, and a force downwards of the wall on the string. And so what this means is in the next instant, you get a wave back propagating. It is reversed, is reflected off of the end, and it's now propagating back towards you. But it's flipped. See, the wave pulse was on top before, and now it's below. So it has inversed, and it propagates back towards us, like this, and going this way, and for completion, get that last one there. Comes back at us. So that's what happens. Very interesting reversal process. And the key here was that the pulse reflects. I'll say inverts as it reflects. There we go. So this boundary here, the wall, the conditions at the end of a wave's immediate journey are called boundary conditions. And the boundary conditions dictate the behavior of the wave when it reaches that boundary. So what other boundary conditions can we have, right? What if, for example, instead of this end of the string being fixed, instead it's attached to a ring on a pole. So there's no more string to the right. So we have this situation now. We have this string, and there's no further string, right? The string ends, so it is a boundary, but we have a pole here. Do this. Pole and we have a ring around it right here that's free to slide up and down, and that's what the rope attaches to. So the ring can go up and down, but it's stuck on that vertical slide, and there's no more string, there's no more rope. So what happens now? So you have a wave pulse, right? Start a wave, and I'm going to do this to denote that it's a ring now. And so then that wave propagates, and it gets closer to the ring, and then it goes here and throws the ring up, because the ring is now kind of sort of part of the rope. So it goes to that peak amplitude and experiences the wave going through it. So it goes up, and I'll do these, and that's the point that it reverses. And so then if you were to follow it here, you would see that the pulse reverses directions back toward you again. But still, still on the top part of the string. So it doesn't invert like it did with the other boundary condition. It instead throws itself back with the pulse at the top. I'll do one more here just to complete it. There. So very interesting different boundary conditions. So there's more to look at here. You know, if you were in this field studying this kind of stuff, and remember, it's not about a string. It's not about a wave on a string. It's about much, much more complex systems where this simple vehicle allows us to study some of the complex topics. So the reason that it reverses without inverting is because the rod here exerts no transverse forces on the string. Whereas before, the wall exerted this transverse force, and so it caused it to invert. And so therefore, the pulse reflects without inverting. It's probably kind of hard to picture why this is kind of interesting, because as we're talking about just string, waves on a string, it isn't that interesting. But if you use your imagination, and maybe in some practice problems or something, you can see some more advanced applications that really utilize this understanding of the behavior of waves. So we just saw the behavior of a wave pulse as it interacts with the boundary. Let's look at a sinusoidal wave, and I promise that there will be more interesting stuff to come out. It's not just going to be another 10 minutes of me drawing a bunch of drawings here that you can predict in your head. So all we're doing now is we have a boundary condition of a wall here, and we have our string again attached, but now over here, instead of just a pulse, we're going to apply simple harmonic motion, right? So an oscillator, like a mass on a spring. So with a wave pulse, the amplitude, this is key, remained constant, and the pulse traveled along the wave, right? The amplitude just kind of transported along the string. But here, with simple harmonic motion, the wave amplitude changes with time, but the wave pattern is going to remain in the same position along the string. So let me see if I can demonstrate what I mean by that. So you have this kind of a simple harmonic motion because you have it tethered here to the wall, and you have a driving oscillator here. And so you have these nodes here and here, and also at the end, I guess. You have these nodes that remain in the same place. So these are nodes. And that just means that their position never moves, never changes. And so this part goes up and then back down. And this part goes down and then back up. But here, at this node, it never changes, right? So the wave is inverting itself left and right of the nodes, but not at the nodes. And then we can also define these maximal points of amplitude change as antinodes. Antinodes, and that's just the most dramatic movement. I won't write that down. And then this length of the string becomes more and more relevant. So this length of this string, you can see because there is 1.5 wavelengths, right? Wavelength would be from peak to peak, and then you have this extra bit here and this extra bit here, right? That means that the length of this string, L, is equal to 1.5 wavelengths of the wave that's traveling through it. So what this is called, with these nodes and the fixed point on the end and the antinodes that are inverting, this is called a standing wave. Standing wave. And this wave does not move down the string. It's just kind of a stationary, standing thing that oscillates in place. As opposed to a traveling wave, standing wave is just standing. So the standing wave, the behavior, is the result of two overlapping things. Thinking back to the principle of superposition, the standing wave is the result of, one, a right propagating wave, traveling wave, from the oscillator to wall, and then also the reflection of that right traveling wave becomes a left traveling wave from the wall to the simple harmonic oscillator. Simple harmonic motion, but simple harmonic oscillator. So I'm going to throw a graphic up here, and I'll also put it maybe in the description of the video here, but I'm going to hopefully have it appear on the page momentarily, and you can trace through the motion yourself, step by step. So take a look at this figure separately from this video and just step through. So look and make sure that it makes sense what's going on from here to there, and spend a second, and you can really see that. So this pink wave here, right? Let me use a better color. This pink wave, green, is traveling that way, and the blue wave, this blue wave, okay, is traveling this way. And as they are doing so, you get different interference between the two, right? So their amplitudes are the wave motion is in each of those directions. So the amplitude of each of those periodic pulses are traveling left and right respectively. But what's key is this gold line here is the superposition of the right propagating wave and the reflected left propagating wave at different times. And so you can see through one full period, right, you can see how it is at each point. And this is that fully destructive interference that we were talking about, where they're exactly out of phase. And so this is then subtracted by that, and you get nothing at all points. No matter what it is, those amplitudes are adding completely destructively. And then here, this situation is complete constructive interference. So you have the maximum addition of the two amplitudes, and so you get the doubling of this superposition wave of both the traveling wave to the right and the reflected wave to the left. So spend a second to go through, and it identifies node, antinode, node, antinode down there. And so you can really kind of imagine the animation of that. And also, a quick Google search can really get a really actual animation going on for you. So now, finally, the last topic that I would like to talk about is a very important one. It explains how music is made. It explains why tones are the way that they are on string instrument. And beyond sound and mechanical waves, it explains normal modes apply to all kinds of waves, electromagnetic waves, everything. So normal modes arise when we have the situation for a mechanical string here. We have the situation where both of the boundaries on either side of the string are fixed. So if we have both boundaries fixed here, then, and we have a string, I'll say this. So we have this length here. If we pluck this string, right, so we pick it up and then let it go, it's going to do this thing, right, through time. It's going to oscillate like a rubber band or like a string of a guitar. If the length from here, length equals the wavelength over 2, right, half of a wavelength, because a full wavelength would be full wavelength would be this similar situation, but with a string length of L equals 2 lambda over 2, if you want to write it that way, right? 1 full wavelength. Well, so that would support waves like this, right? Not very well drawn. Like this, like this. All right, where this is a node right here, and it should be right in the center, but and if you keep expanding that, so what if you have a string of length L equals 3 lambda over 2. Well, now you have an even higher what's called harmonic, like this, where this is a node and that's a node. Or I guess we should be doing this to show that, you know, these are oscillating up and down, oscillating up and down. And so this one would do this, right? Oscillating, oscillating, oscillating. And so what I'm drawing are higher and higher harmonics of supported normal modes. So if we look at this, there must be a node at each end of the string, right? Because we're forcing there to be one. We're fixing it. And so we saw from before even that further nodes come at adjacent half wavelengths, right? That's a half wavelength away, that's half wavelength away from this fixed point, right? So if the string is fixed at both ends like this, and you have some force applied midway, at the midway point along the string to cause that wave, then the length of the string must be multiples of the wavelength over 2. Or maybe a better way to say that is the supported waves that are, the waves that are supported by a string of length L are equal to n lambda over 2 for integers of n, right? So if n is equal to 1, then you have this one. Oops. 1, then you have that guy. N equals 2, then you have that guy. N equals 3. These are higher and higher harmonics that are supported on the string. Yeah. So what this means is this isn't a restriction of the length of the string. It's just for a given length that dictates the wavelengths that are supported as normal modes on the string. Real quick, a mode, right? A normal mode is not the same thing as a node with an N. So a node are these points here, right? Obviously related concepts, but a normal mode is an oscillation pattern that is supported, right, with a given wavelength given a certain length of string. Maybe a better way to put it is to rearrange this and say that normal mode frequencies are equal to 2 times the length over n, where n is our integers again. 1, 2, 3, ... Yeah, so you can imagine going farther and farther and farther, and you get higher and higher harmonics. Along with this series of possible standing wave wavelengths come a series of possible corresponding standing wave frequencies, which is usually how we think of in terms of sound for string instruments, at least. So we have frequencies, that's nu, divided by lambda n. So the larger the wavelength, the smaller the frequency. That's how it goes. The smallest frequency corresponds to the largest wavelength, which is this n equals 1, right? The wavelength is getting smaller and smaller here. And so that's called the fundamental frequency. So when n equals 1, that's called the fundamental frequency for a given system, right? Of a string or of a whatever mechanical wave is going on, or non-mechanical even. Larger frequencies correspond to higher integers of n, and those are called, what I've been using all this time, harmonics, higher harmonics. So in general, if you're talking in terms of frequency, you have frequency is equal to n nu over 2L in terms of length of the string, or n f 1, the fundamental frequency. If all parts of the string or particles of the system are moving sinusoidally with the same frequency, it's called a normal mode of the system, right? So there are other possible vibrations and disturbances and oscillations that are possible in this in a system like this, but if all the particles along the length of a string in this system are moving sinusoidally with the same frequency, it's called a normal mode. because there's infinite integers of n, there are infinite number of normal modes possible for a given system. Larger and larger harmonics, you might imagine, may become more and more difficult to attain. If you imagine n equals 1,000, that would be quite the motion going on with this string, whereas more commonly you would find this fundamental frequency. And I will close with the resounding sentiment that all of this applies to more and more complex physics and mathematics. Normal modes are present in more complex systems than a fixed string, like I've said. And so I'm going to provide an example here of a little thing that you could, a simulation that you can play around with of one of those more complex systems, which you need to know nothing about, but it's just to demonstrate the wide application of this. So I'm going to show you in this video, and then I'll link the link down below, a simulation that hopefully will open up just fine in this browser here. Where are we? Here. All right. Por favor. All right, I will link it down below, but you can see here, you can play around with some of the two of the parameters here, but what this is a simulation of the core, the normal modes that are supported in the core of optical fiber, so fiber optic cable, for linearly polarized light. Obviously, you need to know nothing about the actual physics of what's going on here, but light travels down fiber optic cable due to something that we might hint at later in future chapters. But there are different modes that are supported for the oscillations of light, and it's very complex, and it's electromagnetic oscillations. So we're talking about electromagnetic normal modes here within a tiny, tiny core of fiber optic cable. So go ahead and play around with that simulation, and you can see what I'm talking about. Hopefully that just gets at the complexity of how far this stuff can take you in further physics. Yeah. So if you look past the fact that we have talked all about waves on a string, and you truly master the fundamental concepts that we're talking about that apply way beyond waves on a string, you will recognize that what we're developing here in this class is truly powerful, well beyond this class alone. And a strong grasp of the concepts that I'm presenting to you now in very simple form, using a very simple vehicle like waves on a literal string, will put you in a position to become an absolute master of complex topics that you see in advanced classes, especially electrical engineering, computer science, all kinds of engineering, even mathematics, quantum mechanics, everything. No matter which way you move in STEM, you will come back to oscillations. You will see them everywhere. So please do your due diligence to master these concepts now, so that you're setting yourself up nicely later. All right, that's the end.